Hi, and welcome to Module 2 of Lecture 3. In this module, we're going to have a whirlwind tour of differential calculus. It's reasonable to wonder why I'm going to do that right now. And the reason is having a sort of basic understanding, at least of differential calculus, besides helping in all sorts of ways, is pretty essential to understanding and really understanding what we just did in the previous module, looking at multivariate regression. Multiple regression, rather. And we'll see that by the end of the module, why that is. And it'll also help us in dealing with types of regression that use things like interaction terms or square terms. We'll understand how to interpret those results in a way that's pretty clear when you use calculus and not at all clear when you don't use calculus. So that's why we're going through this. Of course, there's really no way we're going to be able to go through all of differential calculus in like 20 minutes. It's just not really feasible. So the goal here is to give you a sense of the background that we need. If you want more, I've mentioned several times now, I have a math camp up in the same YouTube channel. The stuff we're going to cover today, in this module rather, is a little bit in Lecture 2 under limits, a lot in Lecture 3, and some also on Lecture 4 in that math camp. Anyway, so the goal is to go through this at a pretty high level, and in that we're not going to go into many nuts and bolts, but just to get a sense of what's going on here and how we can use differential calculus to understand better how multiple regression works. Okay, so I'm going to start with some definitions to get a sense of how things work. So, first, the notion of discrete versus instantaneous change. And the instantaneous part is really the basis of calculus as a whole, is dealing with instantaneous or infinitesimal things that are very small or very quick. So, let's take a curve. I'm going to draw like a random curve over here. Here's a line, and here's a curve. There's a curve. Now, you may wonder for this particular curve how it changes with the x, how the y changes with the x. You might wonder this particularly because that's what we've been doing for the past bunch of modules, have been making these regressions models in which you have a dependent variable y that's a function of the independent variable x. There we've been dealing with linear functions. This is not linear. But in general, we've been dealing with a lot of things in which we care about the rate at which y changes with x. So that's the same thing that people care about when looking at differentiation. It's how one variable or one function changes with another variable. So how do we deal with this? Well, discrete change is the rise of a run idea you've seen before. So if I want to know how much y changes between, say, this point and this point, I call this point x1, I call this point x2, and I look up on the plot, and I say the matching point over here is y1, and I look over here in the plot, a line, and the matching point over here is y2. So if I want to know how it changed between x1 and x2, I can take a difference in the y's, and I can divide by the difference in the x's. And that's the discrete change in y given a particular change in x between those 2 points. I could have also written this, which could be useful later, as if this is a function f of x, then it's f of x2 minus f of x1, so it's the function that's represented by this line, by this plot, evaluated at x2 minus the function evaluated at x1, divided by x2 minus x1. Okay. These are measures of discrete change. This is what we call in a sense a secant line connecting 2 points. If you connect the points here, you get something that looks like this. It's a straight line, in this case, under the curve. It connects the points corresponding to the function at x1 to the point corresponding to the function at x2. That's a secant line. Okay, now the question is, what do we do with that? How does that relate to calculus? Well, all differentiation is, in a sense, is taking that discrete change and taking the limit of that change as you get closer and closer and closer to having this x2 minus x1 go to 0. So what does that mean graphically? Let's kind of zoom in on that picture over there. I'm going to try to do like blowing up that one little area over here. That's semi-okay. Okay, so here's your x1, right? And here's your x2. And then here was your y1. And here was your y2. And that's a little higher than it should be. And the secant line looks like this. Okay. Now, what happens if I take x2 closer to x1? Okay, well now, let me change the color here, see if I can make it clearer. Okay, so now, take x2 over here. So split the difference right in the middle there. Now what happens? Well now, it should be higher, so it's not a super great picture here. Now you have a line that looks like this. It's still under the curve, but it is much more steeply sloped. Well, what happens if I go like this? I should use green. Let's go like this and put it really close over here. x3. Well, now it's looking like this. Well, in the limit, as all these x's I'm drawing, and I can't draw any smaller, so I'm going to stop, you get a situation in which you have the curve, and then you have a line like this. Now, what's happening is that the second x you're looking at is getting closer and closer and closer to the first x, and the line you're seeing is tipping further and further up, until eventually, as the x3 is exactly equal to x1, you get what's called a tangent line. A tangent to a curve is a line that intersects with the curve in only one point. And that's what's happening here. As the secant as the distance between the secant points gets smaller and smaller and smaller, you get a tangent at the single first point. That tangent represents the instantaneous rate of change of the function at that single point. That instantaneous rate of change of the function at that point is a derivative of that function at that point. And that's why it's really useful for all sorts of applications. It tells you how fast something is changing at a particular single point as opposed to over a distance. So that's what the derivative is. And we can write that formally by using this definition here. And I'm putting it in a box right now. This is the formal definition of a derivative. And what it is just what we just drew. Let's say x2 that we drew, all those other x's we were drawing are just x plus some h, right? And then we subtract from that f of x. So that is just like this over here on the right, right? x2 here is x plus h, x1 is just x. So you replace this with this. What about the denominator? Well, if the denominator is x plus h is x2 minus x, the denominator is just h. So it's this. So this thing is just that secant line we just talked about, the slope of that secant line. And what we're doing here is just what we did graphically. We're saying as h gets smaller and smaller and smaller, x plus h goes to x, and that secant line goes to the tangent line we drew, and that slope of that secant line, which is given like this, is a derivative as h goes to 0. That's it. That's the whole definition of a derivative. There's nothing else to it at all. And you can actually use the definition to calculate some derivatives in a pretty straightforward fashion. So for instance, I claim that the derivative is the slope of a line at a point. What about if the line is just a line? What if the function we care about is the one we've been dealing with all the time, which is alpha plus beta x? Well, what's the derivative of that? I can plug into this formula, and I get f of x plus h equals alpha plus beta times x plus h. And then f of x is just f of x, so this minus f of x is minus alpha plus beta x. And this thing is just beta h if you multiply out. So the numerator here is beta h. The denominator is h. When you divide beta h by h, you get just beta. So as a limit as h goes to 0, nothing changes because there's no h anymore. So the derivative of the line with the slope beta is beta. That works out how it should, right? We know that the slope of the line is the coefficient on the x, and this formula over here, this formal definition of a derivative, verifies that in fact, yes, the derivative at any point x, because there's no x in beta, derivative at any point x is just the slope of the line, which is beta. That's it. That's all you need to know about this. We'll do some more derivatives though because they're useful, but before we do, I want to get down to some notation. There are many ways to write a derivative. If there's only one variable in the derivative, f prime of x is a way of writing the derivative when there's no confusion about what variable you're taking the derivative of. Df dx is another way of writing a derivative. It means take the derivative of the function f with respect to the variable x. Dy dx when y equals f of x is the same thing. These are all different ways of writing derivative. They're all used interchangeably at different times. You should get used to seeing them. But all they mean is do this. Do this thing in the box. Take the function you're dealing with, evaluate it at x plus h, subtract the function evaluated at x only, simplify that, divide by h, get something or other out of that, and then for that something, take a limit as h goes to 0. What does the limit mean here? The limit means you make h smaller and smaller and smaller until it goes away. In some cases, that's pretty straightforward. So for instance, if I take a limit as h goes to 0 of x plus h, I get x, because the h goes to 0. That's easy. If it's the same limit like this, then that would go to infinity, because h goes to 0, the bottom goes to 0, and anything divided by 0 goes to infinity. So that blows up and the limit doesn't exist. Usually what will happen in the derivatives we deal with are that the first term, the h's in the numerator and the denominator will cancel, and that will leave you with a term with no h that will stick around, and there'll be other terms with h's in them that will go away in the limit. So I'm going to give you an example of that because it's useful in this particular context. So let me write it up here to keep it on the same page for now. So let's say I have a function like we did earlier when we had those squared terms. If you remember back, we had that sleep example, sleep and grades on exams, and we said, you know what, the linear function isn't great. We're gonna use a squared term. So we had something that looked like this. We had beta 1 x, then we had beta 2 x squared. To capture that, I should draw it. This U-shaped curve like this. Right? That was the sleep curve. So, what do we do with this? What's this derivative? What's the slope of this line at any given point? Well, we use this formula again. F of x plus h, this is f of x. F of x plus h equals alpha plus beta 1 x plus h plus beta 2 x plus h squared. So this thing, when you subtract them, the alphas cancel, the beta 1 x's cancel, you get a beta 1 h. So when I do this, I get beta 1 h. Now what about the x squared parts? Well, when I square x plus h, I get x squared, which will cancel with this x squared. So those go away. I get 2xh. So I'm going to write it down over here. And I get an h squared. For the 2, sorry. And I get beta 2h squared. So this is my f of x plus h minus f of x. Now I'm going to divide by h both sides. And that gives me beta 1 plus 2 beta 2x plus beta 2h. And now, as I said, when I take the limit, these first terms have no h. So the limit affects them not at all. This last term is beta 2 times h. So as h goes to 0, this goes to 0. So in the limit, this will go away, and we're left with this. So the instantaneous rate of change of this squared function, this quadratic function, is equal to beta 1, which is the slope of the line by itself, plus 2 times beta 2 times x. So the slope of this thing is going to be changing as x increases or decreases. That's what we see over here, right? As x increases, the slope of this line decreases, right? It gets gradually less and less positive, and then eventually becomes negative. That would be consistent with having a beta 2 here that was negative. As you start off with a positive slope, so beta 1 is positive, as you increase x, you get the slope gets smaller and smaller and smaller, which will be consistent with a negative beta 2. And that's exactly how we go about making hypotheses for quadratic variables. If we claim in some theory that we believe these things increase at first and then gradually decrease, we say, my hypothesis is that the theory looks like this. There's a quadratic term in my independent variable. I think beta 1's positive, I'm going to hypothesize. And I think beta 2 is negative, I'm going to hypothesize. Then you would go and you would test with your data and to see if both of these terms are actually what you expected them to be via data. So that's how it works. And again, I don't expect you to sit down and watch this for like whatever it's been so far time-wise and be like, oh, I get it completely. It makes total sense to me. Differentiation is easy. Rather, I want you to get a sense that this is not some magic, right? These derivatives tell you the rate of change of your function at a given point. They all come from the exact same definition. And in fact, if you go on, if we look at some of the math videos I have, I will derive a lot of the properties of derivatives from the same definition. So there's nothing fancy about it. It's the same thing over and over again. There's a bunch of algebra and moving around terms and subtracting terms that you have to deal with first. But it all comes from the exact same formal definition, and that's all it is. The interpretation of that is just the instantaneous rate of change of a function at a particular point x. That's all it is. Before I do the last bullet point here, which is the most relevant for the multiple regression stuff we just did, I want to first show you one more thing, which is interaction terms, because this will come up at the beginning of lecture 4. So let's say I wanted to have a situation in which the rate of change of the function of y, the dependent variable, with respect to x, was a function not only of one variable, x1, and not only of a second variable, x2. Actually, you know what? I have to take a aside there. I don't know. I'll keep going. Sorry. x2, but also of the multiplication of x1 and x2. How do we do that? How do we deal with that? We'll talk about what that means more in lecture 4, but the idea is as I increase x1, I'm not only going to have a direct effect of x1 through this term, I'm going to change how x2 affects y through this last term. Now to do this, I have to introduce what's called a partial derivative. A partial derivative is often written like this. Instead of a d, it's like that, called a partial, and it'll be df over dx in this case. Or df over dx1, because you have to specify which of the variables you have. You won't use a partial if it's just only one variable. So, how do I do this? Well, the way you calculate a partial derivative, and this ties directly to multiple regression, the way you calculate a partial derivative is by taking the derivative of your function in the exact same way we just did, while treating everything else as a constant. That should sound familiar, right? You're going to take the derivative of the function with respect to the variable you care about, while treating everything else as a constant. So the interpretation of this partial derivative is it's the rate of change in f, the function f, with respect to x1, treating every other variable in the function as a constant. That's exactly what we do when we interpret the coefficients in a multiple regression. Each coefficient was the rate of change in the dependent variable with respect to the independent variable, multiplying that coefficient, holding all the other independent variables you included in the regression model constant. And I'll show you why that is right here. It's because the partial derivative is defined that way, and the partial derivative tells you the rate of change of a function with respect to a particular variable, holding all the other variables constant. So here we do is take a derivative of each individual point. We can plug it in here to do, so let's just do that. So we have the limit as h goes to 0 of f of x plus h. Now it's f of x1 plus h. That's the only thing that varies here is x1. Everything else is a constant. So we have alpha plus beta 1 x1 plus h. Now this beta 2 x2 is just a constant in this context. It doesn't have any variable meaning as a variable. It's just a constant. And then beta 3 is a constant. X2 over here is a constant. And we have x1 minus h. Sorry, plus h. Right there. We subtract from this alpha. And we subtract beta 1 x1. And we subtract beta 2 x2. This is the regular function by itself. And we subtract beta 3 x2 x1. And we divide that whole thing by h. Now that equals the limit as h goes to 0. The alphas cancel. The beta 1 x1s cancel. The beta 2 x2 cancels. And the beta 3 x2 x1 cancels. And that leaves beta 1 h plus beta 3 x2 h divided by h. The h's all cancel. So we get rid of all these. And we're left with a limit of h goes to 0 of beta 1 plus beta 3 x2. There are no h's, so this is just beta 1 plus beta 3 x2. And this tells us how interaction terms work. The way they work is the rate of change of f with respect to x, holding all the other variables constant, is equal to the coefficient on x1 directly, plus this beta 3 times x2. So as the other independent variable changes, it changes the rate in which x1 affects f. So x2, the interaction term, means that the variable affects not only y directly. Changes in x2 don't only affect y directly, but they also affect the way in which x1 affects y. If beta 3 is positive, as I increase x2, y responds more strongly to x1 than it did before. If beta 3 is negative, as I increase x2, y responds less strongly to x1 than it did before when x2 was less. So x2 can affect the slope of the line that represents the rate in which f changes with respect to x1. We'll talk more about this when we discuss in lecture 4, but I wanted to show you this now to give you a sense of how, by sort of having even like a 25-minute long basic understanding of differentiation, can help you understand how we interpret all these multiple regression coefficients and how we can do more complicated regressions without losing track of what we're doing. And the key is the interpretation of the partial derivative right here as the rate of change, the instantaneous rate of change of a function. In this case, the function is your dependent variable model, as a function of a single variable holding all the other variables you included constant. That's why you interpret all the betas like that. So if I didn't have this interaction term, if I stopped right here, then the derivative would just be beta 1. This would just be beta 1 for the same reasons as down here. And we'd see that the rate of change of f with respect to x1 holding x2 constant was just the coefficient on x1, which is beta 1, which is exactly the interpretation we gave for the coefficient on the independent variable in the previous module for multiple regression. This is exactly where it comes from, and knowing that can help you interpret more complex models like ones with interaction terms or squared terms as well, or even more complex things. They all follow from this same rule and the same definition of a partial derivative. That's it. No more of differentiation for now. Next time, we're going to talk very briefly about matrices, mostly because they're used for capturing and holding and storing multiple independent variables, and you can use them to solve for your regression coefficients, and we'll talk about that pretty briefly next time. Thank you very much.